Okay, let's start. So our first speaker in this afternoon session is Professor HuaXing from Peking University. He's going to tell us something about energy operators in particle physics and quantum field theory.
Okay, thank you very much for the introduction. It's a great honor to be here and to tell you about my recent research. So as you can see, this talk will be about energy operators. I will explain what it is. The research that I did most often is study the particle collision at Large Hadron Collider. This is one of the typical scattering events at Large Hadron Colliders. What you can see here is a lot of hadrons produced in a hard collisions. They are produced from, in the very short distance, there is a quark and gluon scattering. After the hard collision, the quark gluon will decay into, split into lots of quarks and gluons. And at some stage, these quarks and gluons will hadronize into the hadrons. The hadronization happens at a time scale of 10 to the minus 20 seconds, around 10 to the minus second. So it's not, you cannot see that in this experimental figure. There are several key questions we are interested to understanding. The first one is use this experimental setup to understanding strongly coupled gauge theory. In particular, in this case, this is QCD. The particular question that that's still open is how does quarks and gluon evolve into hadrons? The second question is how to use these many particle scattering events to do precision standard model measurement as well as probing new physics. For example, how to extract standard model parameters from this very complicated final state, or how to calculate this process to very high accuracy in order to find new physics. This naively, you can just do a S-matrix calculation to get a cross-section for this process, but that's impossible because you can see this involves many particles. Involve tens or hundreds of particles. And also this process is intrinsically non-perturbative. So this is not an option for a practical purpose. This question actually has been asked, or it's there since the very early days of QCD. The standard paradigm is the so-called using jets to study those processes. The idea of jet is first proposed by Sturman and Weinberg in a classic papers. The idea is the following. Although you are dealing with a multi-particle collision event, but you can reduce the number of particles by first cluster these particles into jets. A jet is a bunch of hadronic particles along some directions. In this case, you can see there are clearly two particular directions that you can group those particles together to form two jets. And then once you have these jets, you can actually calculate the property of the jet distribution using just quarks and gluons. The leading order calculation would just, for example, would just involve a quarks and anti-quarks. But if you can systematically improve your precision by including additional radiation or virtual corrections. In this case, you can do precision calculation for the jet cross-section and compare with experiment. This is a very important tool at the LHC physics. It has made tremendous success both as a discovery tool as well as a precision measurement tool. As you can see, one of the standard definition of jet has been accumulated like 10,000 citations. Basically, every experimental paper as well as theory paper on LHC physics will cite this paper. However, there's also a drawback of this approach to study strong interaction. One drawback is that the definition of jet is not unique, and certainly there's no concept of jet at the level of standard model Lagrangian. And in particular, when you define a jet, it necessarily involves certain algorithmic definitions. This algorithmic definition makes any analytic calculation for jet property very difficult. So the questions that people ask is there an alternative way to measure this high multiplicity process as well as calculate property for this high multiplicity process? And the answer is yes, and actually it's also considered around the same time. There's a paper by these gentlemen in 1970s they define a observable called energy correlation, which I will explain what it is. But you can see this idea is actually not favored by experimentalists and theories after the very few years when it's discovered. But recently, there is a research interest in this observable as a tool to study strong interactions. There are several reasons why this is a nice observable for studying the high multiplicity event. One of them is that you can express this observable in a very compact and simple way. In particular, in E plus E minus collider, if you look at the two-point energy correlator, it can be written as a 4-point function. And also, you need to do some Fourier transform to it. But it's very simple. It's just a 4-point function. So that makes very close connection to the recent development in understanding 4-point function in conformal field theory. So this is one of the very important reasons why it received renewed interest. But as you can see, for high energy collision at the E plus E minus, for example, the multiplicity, the typical multiplicity is not that high to make it a statistical system. It's like 10 particle, 20 particle, for example. So when measuring a correlation function event by event, if it will not be continuous, in other words, it's difficult to actually predict this observable event by event. But once you accumulate a lot of scattering events, ultimately you will get a smooth distribution. And the question is whether one can predict, make a theoretical prediction for this distribution, and the answer is yes. So this is a distribution of the energy correlation. The x-axis is the angle between two detectors, and the y-axis is the weight of the product of the energy that you receive in those two detectors. This is a definition, operational definition you can write down. As you can see, there's an interesting feature in this distribution. First, there's a peak in the 0 degrees, which you can understand from these scattering events because at small angle, there's a lot of energy flow. You can also see a peak in the 180 degrees, which you can also understand from, for example, this scattering event, because by momentum conservation, there will be a large correlation between 180 degrees detectors. Both of these limits are very interesting. But for this talk, I will mostly focus on the 0 degrees case. Okay, so one of the reasons that this energy correlator become interesting to many people is that you can have a dual field on this observable. The traditional view is that in the bulk, we have a quark produced from hard scattering, and it keeps radiate gluons, and the gluon can also split into quarks. At some energy scale, at some low enough energy scale, these quarks and gluon will hadronize into hadrons and detected by your detectors. This is one way to understand it, and we also know how to describe this process using the celebrated Diglab evolution kernel, P, the splitting function P. Another way to understand this process is just think of your detector as some operator in quantum field theory. In particular, in this case, this operator will be a non-local operator sitting at now infinity. And when you are looking at the energy correlator at a very small angle, it turns out that people can develop a kind of operator product expansion to describe the small angle singularity for this distribution. So there are two dual ways to describe the same process. And actually, these two dual ways to describe the same process is very useful. There are many concepts which is independently developed from the different approach, but they are actually related in a very non-trivial way. And these actually teach people a lot about quantum field theory itself. In this talk, I will not talk about all of them, but we only talk about a few of them. The one thing that I find very interesting is that when you are putting to the detectors very close to each other, your distribution will exhibit a scaling behavior. And this scaling behavior, when interpreted in terms of this picture, will be solved by a Digleb evolution equation. This phenomena actually has been very recently confirmed or confirmed by the experiment. This is a very interesting progress. Then I will talk about how to generalize this picture by putting more detectors on your more energy detectors on this celestial sphere, which would corresponding to multicollinear splitting in this picture, but in the other picture, there's a nice language in terms of conformal block expansion, decomposition to describe the same thing. And then I will also talk about how to use the language from this side to discuss perturbative and non-perturbative power correction for this observable, as well as how the phenomenological driven consideration from this side can lead to a new structure that hasn't been studied on the right-hand side. So that's the plan of my talk. So let me start from the definition of the energy operator. The energy operator is defined as the integral of stress tensor at now infinity. What it does is that you put a detector at a large distance, and then you integrate it over time. The hard collision in the center of the space-time will radiate a particle flying recorded by your energy, by your detector, and that's what's actually happening at the real experiments. The same detector can be written in a orthogonal way. If you exchange the integral with limit, then you can write this same operator in this way. This way makes the symmetry manifest. So this would be the simplest, actually, this is called a line rate operator because you are integrating an operator along a null line. And it's actually the simplest line rate operator that you can measure at asymptotic infinity. So many of the measurements that I'm going to talk about will be done using this operator. And I would like to think about measurement, doing measurement using this operator as a way to study the Regge trajectory of high energy, high multiplicity scattering. The Regge trajectory is a very important concept in the early days of QCD, where people found that the line-lowing hadrons, they actually lie on a line in the angular momentum and mass square plane. For the high energy scattering, there's a similar story here. In the free theory, if you're looking at the local twist 2 operators of quarks and gluon, they will sit on a straight dashed line. But because of interaction, they will deviate from the free theory. A very important goal for perturbative QCD is actually to measure the deviation of this operator from the free theory, which the deviation we will call the enormous dimension. In this case, there's an enormous dimension gamma 4 for a spin 4 operator here. And the story so energy correlator itself is sitting here, where the stress tensor is sitting here, and after light transform, it becomes the energy detector at now infinity. But we are interested on the other operators here because they can receive quantum corrections. Very interesting way to actually measure their quantum correction is through energy correlator. For example, if you measure a 2-point energy correlator, you can actually probe the distance of this operator with the free theory line. If you do a 3-point energy correlator measurement, you will be able to probe this enormous dimension. So doing the measurement in this way is like decompose your theory into individual local operators. So we know that in the standard quantum field theory, a very important result is the Euclidean operator product expansion. The operator product expansion will allows you to express any correlation function as by iterative doing this OPE, you can reduce this n-point correlation function to just 2-point correlation function. In the case of energy operator, there's also a similar kind of operator product expansion being developed in the past 10, 20 years. The idea is that when you put two detectors close to each other, they can be OP into a third Lyrae operators on the now infinity. And there is a computable, calculable, non-enormous dimension or scaling exponent denoted as tau I here. So this is very nice because if you think of your measurement as being performed, if you think of measurement as done on the celestial sphere, then this is like a, it's real, the OPE is really like form a fictitious two-dimensional Euclidean CFT on your detector sphere. If the space of the Lyrae operator on this sphere is completely known, then in principle, any n-point energy correlator can be built out from just 2 points. So that will give a very nice way, alternative way to do calculation. Yeah, so the operator OI is an integration of a local operator, a Lie transform actually, a Lie transform a local operator. It's kind of similar to the energy operator where the O would be a stress tensor. But now you have a higher spin twist 2 operator.
Actually, I'm more interested in the fact whether that can be computed in Euclidean space-time directly.
So at this moment, I don't think it can be computed in a Euclidean lattice theory because this operator is essentially living on a future now line. So its definition is intrinsically Minkowskian, Lorentzian. Yeah.
So let me try to understand. So here, each operator is something like a time integral, right?
Yeah, they are integrate over time. So in other words, it's average over the scattering, basically. Yeah. Okay. So using this language, you can actually understanding where this scaling law comes from. By the scaling law, I mean when you look at the two energy detector, you put two energy there very close, you will see that there will be a scaling law in the leading term of the OPE. So the way to understanding this is the following. This is the definition of this Lyrae operator I'm putting here, and this part is the Lie transform. This OPE formula is completely fixed by symmetry. So basically, the first step you can do is to count the dimension between the left-hand side and right-hand side. On the left-hand side, you have two energy operators, so the dimension is 1 plus equals 2. On the right-hand side, the angle doesn't have any dimension, so all the dimension comes from this Lyrae operator. You can do this math and found that the Lyrae operator has dimension j minus 1. So using this formula, you fix that the operator that appearing on the right-hand side of the OPE must contain a local operator with spin j equals 3. Then using this information, you can do consider another quantum number, which is the collinear spin. The collinear spin is related to a boost quantum number in the n-bar directions. In this case, you can count the collinear spin of each operator, which I gave the formulas here. So it's a very simple algebra. But the key point here is that the theta also has the boost quantum number, gamma in this case. So you can uniquely determine the gamma because you already know J. You can completely determine gamma from this formula, which is minus 2 plus. X is minus 2 plus gamma. So in this way, so this formula is completely determined by symmetry. So this is very interesting. Back in 2008, when Malosina and Hoffman, they first write down this OPE formula. He gave a talk at Santa Barbara, and Poczynski. Scaling law is always very interesting. So Poczynski asked, because there's a lot of QCD data, the question is whether one can actually see this scaling behavior in real data. Unfortunately, at that time, the answer is no. And the reason is that there are several reasons. One of the reasons is that the experimental resolution is not good enough to actually look at the small enough angle. The other reason is that the theories doesn't have a resummation formula to actually describe that region very well. So for the resummation formula that my collaborators and I worked out the resummation formula for the collinear limit a few years ago. I'm not going to describe this formula in detail, but the key point is that in addition to the scaling behavior, this paper, we also study how a running coupling would modify the scaling behavior. And the key point is that the QCD, the correction from higher order actually is very large. As you can see here, from leading log to next leading log to next log, actually is a quite big jump. So this also explains why in the early days the experimentalist is not very interested in measuring it, because without the precision theory prediction, it's really difficult to get useful information from the measurement. But now, given that we have high accuracy prediction, it's now actually possible to do the experiment, not at the lab, but at the Large Hadron Colliders. So this is a measurement from the CMS collaborations. They look at the high PT jets, and they look at the energy correlators inside the jet. What's interesting is that they do observe a perturbative scaling region, which is shown in this region. This region is, as I said, this region is completely described by the OPE of the Lyrae operators plus the running coupling effects. And I will come back to this part later. But what's interesting is that experimentally also confirm the existence of a region that show another scaling behavior. This scaling behavior is the typical behavior of free hadrons, which you produce a lot of hadrons. They have no correlations, and because of no correlation, they show a scaling law in these regions. And what's also interesting is that between the perturbative region and the free hadron region, there's a transition region. The transition region will corresponding to the hadronization that I mentioned earlier in the talk, which we still don't know how to describe this region, but right now there is a experimental data for this region. And also, as you can see, there are different event generator comparing to actual data. They are not doing very well in this region, which means that there's actually this observer can actually probing the difference of the different mechanism of the hadronizations. Okay. I also told you that a two-point energy correlator will probe a spin 3 local operators. But you can also do higher points. For example, you can do a 3-point energy correlator. It's quite complicated because it involves 3 angles, but if you just project it to the largest angle, then it's still become a one-dimensional observable, as you can show here. Then you can form a ratio of 3-point and 2-point, 4-point and 2-point, etc. And this ratio, because individual correlator is a scaling law, which the scaling exponent depends on the enormous dimension of the local operators. Then the ratio will also depend on those enormous dimension. But the benefit of the ratio is that it cancels a lot of non-perturbative effects, and many of the effects that's difficult to control analytically. What you can see here is the ratio of different points from 2-point, 3-point to 6-point. And as you can see, as the number of points increase, the slope actually increase. And that's actually expected from this figure, because with the higher spin, your operator is having larger enormous dimensions, as shown by this Reggie trajectory. So this provides a very useful experimental data to measure one of the important parameters in the standard model, which is the strong coupling. By CMS experiment, by comparing the slope of 3-point versus 2-point energy correlator, they are able to extract a strong coupling that's up to this stage is actually the most precise strong coupling measure from jet substructure. If you put it in the world average of the strong coupling measurement, it's not yet it's not yet aligned with the central world average, but at least it's uncertain. It's within the uncertainty band. But this set out a very concrete goal for further reducing the theoretical uncertainty for this measurement. Here is another interesting outcome of this measurement. This is the slope of the 3-point versus 2-point energy correlator as a function of the PT of the jet. As you can see, as you increase the PT of the jet, the slope actually decreases. The reason is that the slope is proportional, roughly speaking, proportional to strong coupling. So as the PT increases, the strong coupling also decreases. That's why you see the slope becomes smaller and smaller. If you have infinite PT jet, this slope will actually be 0. If you combine all the slope in across different PT jet, you can actually see a behavior of asymptotic freedom. But this behavior of asymptotic freedom is extracted from a single observer that everyone can see and can understand what is happening here. This is study the energy correlator inside the jet, but actually the definition of jet is not important. As long as you have a bunch of particles in one direction, you don't actually need to define the jet boundary to do this measurement. Yeah. The angle is in the x-axis. Yeah. The XL is angle square. Oh, sorry. So the E3C depends on 3 angles actually, but we are projected to the largest angle. So we are integrated over the small angle. They are not particularly important in this case. Okay. So now let me, speaking about the 3-point correlator, let me move to higher point. Higher point correlator is very interesting in several sense. The one particular reason is that you can calculate the higher point correlators. This is non-trivial because the usual for a 3-pronged jet substructure, it's very difficult to calculate analytically. But in this case, if you consider the 3-point in a collinear limit, you can actually get a fully analytic results for it. This is not a result of QCD, but it's a clone cousin of QCD. And the QCD result is more complicated, but the typical structure is the same. You can also do the calculation for even higher point. That was done recently by a team of researchers. And that's not me. Yeah, that's the student of Kai Yan. But this actually provides very helpful data to study the structure of higher point energy correlators. One particular structure one can study is considering the perturbed and non-perturbed power expansion. There are 2 ways to expand the observable. One way is that if you have 2 detectors, you can consider the expansion in the angle. So when you're expanding this way, this is actually a twist expansion. The twist would count is the twist of the local operator that being light transform. You can also do a non-perturbed power correction, which is in power of lambda QCD over Q. In both expansion, the symmetry will plays a very important role to help us understanding the structure of the observable. Let me start from the twist expansion. One very interesting limit is that you can look at the squeeze limit of the 3-point energy correlators. So this is also, I think, being considered in cosmology context. Because we can calculate this 3-point correlator analytically, so you have lots of data about this squeeze limit. One interesting limit that you can, when you actually do the expansion, you see pattern emerge from this particular limit. For example, if you look at the series expansion in theta s, there will appear some phi dependence. Namely, when you rotate 3 and 2, there will be some azimuthal dependence in this expansion. And interestingly, this expansion can be summed to all orders in terms of a single hypergeometric functions. This means that there must be an underlying symmetry reason for this term to be able to resum into a single terms. And indeed, there's a symmetry reason behind that. For the 3-point energy correlator, you can actually thinking of it as a 4-point function. There are 3 energy detectors, but there's also a source, a sink, that create and annihilate the energy flow. For this particular 3-point correlator, it is Lorentzian invariance. The action of the Lorentz generator on the celestial sphere actually is identical to the conformal transformation on the celestial sphere. So you can use these effects to derive a differential equation that's obeyed by this 3-point correlator. And it turns out that this differential equation is exactly the Casimir equation for a 2D conformal field theory, so that you can use everything that people learn about 2D CFT to study this 3-point energy correlator. In particular, you can expand this 3-point correlator in terms of the 2-dimensional conformal blocks. This is one example of, for a particular channel, you can expand the results in terms of this conformal block. Each of these conformal blocks will be a function of the angle of the angle of the triangle, the 3 angles of these correlators. However, they have different importance. The most important will be those blocks with the lower dimension, delta here, the number 4 here. And the higher term you have will be less important. This can be explicitly shown numerically. So this is the plot of each of those kinematical data for different twist and different speed. As you can see, so this is the full QCD calculation at leading order. So this plot, so I have mapped the 3 angle into to a plane. So this will corresponding, this line will corresponding to the squeeze limit. This line will corresponding to the folded limit, and this will corresponding to the equilateral limit. As you can see, you can describe the full shape of a 3-point correlator using just a single twist 2 conformal block. So this is very nice. You can actually, once you calculate the coefficient for these blocks, you can already describe the shape pretty well. However, this is just QCD in vacuum. You can imagine that there could be more complicated situation where a single block cannot describe well. For example, in heavy ion collision, there are many effects going on in a heavy ion collision. When a jet is produced, it can interact with the medium, and it can also lose energy to the medium, and there could also be induced radiation due to the medium. And all of these effects is very complicated, and it's very useful tools for studying QCD. One example is the phenomena of jet wave. The phenomena of jet wave is this is a illustration of what this phenomena means. Think about a duck flowing in a water. The water is your medium. As the duck swim in this direction, it actually creates some depletion of water in this region. At the same moment, it will create some enhancement of particles in this region. So the question is whether you can actually see this. So this is an example, but this is also what's actually people believe that would happen when a jet went through a UP, quark gluon plasma. And people actually, very recently, this is a paper in this week, they actually look at this 3-point correlator in a, go through a QGP. And this is the shape of the 3-point correlator. If you remember that in the vacuum, this is very different from the vacuum. In the vacuum, the equilateral triangle is, in that limit, it's significantly damped or suppressed. But in this case, you see a enhancement in that limit. Just look at this, it cannot just be described by a single twist 2 operator. Maybe you need higher twist operator to describe this. What I want to show here is that by looking at looking at higher point correlator more differentially, it is possible to probe a very interesting phenomena that's hard to probe otherwise. Now let me come to another direction of expansion, which is the non-perturbative power corrections. The expansion in this line is very important to control the theoretical accuracy for your observable, for which you can see from this line. So these are the 2-point energy correlator, but plotted at hadron and parton level. By parton level, I mean you calculate the energy correlator using just quarks and gluon. Of course, in the real world, you do not observe quarks and gluon, so it cannot really describe the real data. There need to be some hadronization corrections. And as you can see, I would define this hadronization or power correction as the hadron level calculation minus the parton level calculation. This calculation is done using a event generator. As you can see from this plot, this power correction actually is very large. It can reach like 50%. So it's very important to control this power correction if we want to extract alpha S to a higher accuracy. It turns out that this power correction can also be understood using the Lyrae OBE that I mentioned before. I told you before that the leading term in this Lyrae OBE is completely controlled or determined by a symmetry argument. Now it turns out that the second term is also determined by symmetry argument. Once you assume that the second term is proportional to lambda QCD. Because the lambda QCD carry a specific quantum number, you can do the calculation like for the leading term again, and you will find that if you for this term, if you behave as theta to the third power or x, so xl is actually theta squared. So this will correspond to theta cubic term. The key assumption here is that the hadron. So this calculation is just using symmetry argument. There's nothing. And the key assumption here is that the hadronization scale is actually boost invariant. So this is very nice. We can, because by symmetry we know how the power correction actually the scaling behavior of the power correction is fixed by symmetry. We can actually look in the great detail of the power correction itself. So this plot is what is showing is the power correction. So it corresponding to the hadron level prediction minus the parton level predictions. You see that it also exhibits a scaling behavior, just like leading power that I showed you before. And you can remove the classical scaling behavior by multiplying this distribution by the classical piece. What is left will corresponding to the quantum corrections to this to this classical scaling behavior. This is not real data. It's still a simulation done using Herwig. But you can see that there is a non-trivial shape of these functions. So in other words, the prediction that the scaling behavior is XL to the 3/2 is not exactly true. There will be some trivial corrections to this function. That's true. HuaXing is only a model. So ultimately, it would be, we cannot trust HuaXing because this is something that, in particular, in this region, the modeling in HuaXing is different from the modeling in Pythia. So we should not trust it. But this is, but at this moment, since we don't have experimental data, so this is just, this is the only thing we can play with. But certainly, it will be very interesting to measure this behavior experimentally. So what I want to tell you is that there are two kinds of you can think that there are two kinds of behavior of this curve. The first thing is that this curve is not flat in square root of XL times Q. It has some shape in this direction. The second thing is that this curve would evolve in energy. So by doing experiment at different energy, the curve actually shifts. So what I want to do now is try to using symmetry to determine the Q dependence of these functions. And the idea is actually very simple. If I define all the rest of these terms as a power correction, which I write in the left-hand side, then there are actually two pieces in it. The first piece is a non-perturbative coefficient functions, which could depend on lambda QCD as well as some intrinsic perp scale K, which I denote as K perp. And on the right-hand side, it will be a matrix element of the Lyrae operator, which is perturbative and calculable. It depends on Q as well as a factorization skew mu. Now, because the full distribution cannot depend on mu, so the mu dependence must cancel between the left-hand side and right-hand side. Because the right-hand side is actually perturbative, you can actually you know what is its scale dependence. The scale dependence is actually proportional to the Diglab moment, the moment of Diglab splitting functions. Using this equation, you are able to determine the scale dependence of this non-perturbative D function. Solving this function, you will be able to completely fix the Q dependence for these non-perturbative coefficients. So that's another thing one can learn from Lyrae OPE. So here I'm trying to tell you what this non-perturbative function actually tell us about. So the non-perturbative function depends on a momentum scale K perp. The K perp is related to the energy times the angle. So it's actually a momentum scale, the scale of momentum exchange between the particles. So this non-perturbative function, as a function of K perp, you should think of it as a describing the non-perturbative physics when the parton hadronize in different angle scale. This will be a new set of a non-perturbative function one can try to extract from experiment. But right now, this is very new and we can only play with the data. So one way to see that as I told you, this non-perturbative, the Q dependence of this non-perturbative function can be described using perturbation theory. And these two plots show you how good the prediction is. So for example, if you look at this plot, the three curves corresponding to the same observable, in this case would be E3C at three different energy. So what I did here is to fit the green curve, for fit the green box using this green line, and then make a prediction for the blue curve and the red curve. And you can see that the agreement is pretty good. However, if you look at, this is for the E plus E minus to QQ bar. If you look at the H decay to glue, for the 3-point correlator and 4-point correlator, the agreement is pretty well. But for the 2-point energy correlator, you can see that the agreement is not particularly well. The reason is the following. When you consider the 2-point energy correlator, you can do the power expansion systematically, one by one. You can continually go down this line. At the lambda square terms, the line rate operator appearing here will corresponding to a local operator with spin j equals 1. And then the scale evolution of this part with corresponding to the norms dimension of j equals 1. However, the norms dimension of j equals 1 actually is singular. This singularity, of course, is well known. This singularity is corresponding to the small x singularity. The appearance of this small x singularity could explain why we see that for the 2-point energy correlator, the description is not good enough, but for 3-point and 4-point, they have a good description. Okay. But there's another way to do the fitting. As I told you, this evolution, all the Q dependence actually is hidden in these scale evolution factors. And in the 2-point there's a different way to when I do the fitting here, I actually use both the quark and gluon to do the fit. For example, when I do experiment at 250 GeV, I will have to fit a non-perturbative function for the quarks and gluon simultaneously. That, of course, is you cannot do that with lab, because lab only has E plus E minus to QQ bar. It doesn't have gluon in it.
Sure. So what do you want? So the solid curves are from Q curve, right? Solid lines.
Yes. Sorry, the solid line is from fit. So the line in the central is a fit to the dot. Yeah, the dot is a Herwig.
So because there's something that the non-perturbative part you don't know.
Yeah, this is the fitted green line is what I don't know. And but I want to once fitted, I want to predict its behavior at different energy scale. And what is showing here is that you can actually predict the running pretty well. Yeah, just like a pattern different, but here for a different kinds of final state fragmentation process. There's a different ways to do the fitting, not using simultaneously quark and gluon fragmentation, but just using the quarks fragmentation at 2 different energy. So this is now I'm changing the strategy of fitting. I'm using the middle 2 lines to fit my non-perturbative function, and then I use my RG evolution to predict the blue and the black line. You can see that for the quarks, the agreement is pretty good. For the gluon, the agreement is also good. I showed you before that the other way of fitting doesn't predict well the energy, 2-point energy correlator. Do a fitting in this way, you can actually predict it quite well. Okay, in the final 10 minutes, let me tell you another application of energy correlators. So far, I have been only talking about measuring energy correlator in the final stage, but as many of you probably know, there will be an electron-ion collider built in the United States. This collider will be dedicated to the study of strong interaction and nuclear structure. So the question is whether we can use energy correlator to probe the structure of nuclear in this detector. This is event is displayed of EP collider, but not at EIC yet. It's a Hera event display. As you can see, that you can also clearly see the production of jet in a EP collisions. There are actually two kinds of jet in this case. One is called the current fragmentation jet. This jet is arising from the quark photon in the action. There's another target fragmentation jet, which is dominantly coming from the proton, initial state radiation. So the question here is that whether we can, by doing measurement in this target fragmentation region, whether we can probe the structure of the proton. So one can define an energy correlator in a very similar way. You have a proton coming in. You have proton coming in which scatter. There's a quark scatter with a photon, but there's also initial state radiation in the beam directions. Then you can measure the energy correlator in this direct. You can measure the energy weighted angle correlation. Now the angle will be the angle of the forward detector with respect to the beam directions. This observable, you can write down an operator definition for this observable, which corresponding to the insertion of energy operator inside a PDF. So without the E, this will correspond to the usual PDF. Usual PDF will corresponding to an integral of a 2-point quark anti-quark correlator with some Wilson line extended to infinity. But now I'm trying to measure the energy flow from this Wilson line and also from this quark line. So the idea of that, the reason that this measurement can probe the structure of the nucleon can be explained in the following way. The usual way to probe the structure of a proton is to look at the hard parton that entering the hard scattering. This is the by measuring the momentum fraction of this parton, you can see how momentum is distributed inside the proton. So this would be corresponding to the usual definition of collinear PDF. On the other hand, you can also measure the energy distribution of anything that's not going into the hard collision. Because the initial proton state is actually, you can write it as the sum of this hard parton as well as anything else. So in principle, you can extract all the information about psi by doing measurement in X. So that's the basic idea of the nucleon energy correlator. And you can actually show this equivalence explicitly. For example, the moment of TMD PDF would be equals to the certain moment of the energy correlator measured in the beam directions. And actually doing this measuring in this way actually has a benefit. When people discuss or define the moment of TMD PDF, it's actually there's no canonical definition of what's the boundary or upper bound of your integral. However, if you do this measurement using the energy correlator, there's a well-defined boundary for the radiation that you should measure, which would corresponding to the target jet in this region. So it provides a useful way to actually measure the moment of the TMD PDF. Here is a simulation of the nucleon energy correlator using fixed order perturbation theory. As you see clearly, at very small angle, the nuclear energy correlator exhibits a scaling law. So this is the leading order prediction, which would, in this log plot, would corresponding to a constant. And next to linear, it becomes a alpha s squared times log squared, and that's shown in the here as a straight line. This behavior is very similar to the usual Digger evolution for the PDF, but it's explicitly shown in the angle, not in Q. So this is the usual scaling behavior of the scaling violation of the Parton distribution function. But now you can do very similar measurement using a nucleon energy correlator. The scaling region will corresponding to the flat region in these lines. One very interesting thing that one can consider is what I showed you before. In the case of jet, there will be 3 different regions one can experimentally observe. First, there's a quarks and gluon in the interacting region. Then there's a hadronization transition region. And finally, there's a free hadron region. In the case of nucleon EEC, you can also expect the appearance of 3 different regions. First, there will be a scaling region, which can be predicted by perturbative QCD. And then there will be a free hadron region, which you can also predict because it's free hadrons. However, what is not known is what will be happen in the middle. We don't have experimental data, and also we can only, so this is a plot from just physics simulation. But you can see that this behavior is quite different from the fragmentation case. So the interesting question is that whether this different structure would would encode the information of the nucleon structure in it, which we don't yet have an answer, but it would be a very interesting question to study. A different physics one can probe is the small x gluon saturation physics. This is the PDF that you probably know before. As you can see, the gluon Parton distribution is rising very fast at small x, which means that at small and small x you can get more and more gluons. But ultimately, you will get a saturation. Because the gluon density cannot just diverge. It will saturate at certain point. Using the energy correlator, we can probe this behavior by doing a simple model calculation. What we find is that instead of scaling behavior the usual behavior is that there's a scaling law behavior. However, when you are entering the saturation region, this 1/theta enhancement will be gone. So we are not going to see the small angle enhancement. So this is a plot using model calculations. So this line corresponding to the proton, where you don't expect to have saturation. There's no separation happening. The saturation scale is just too low. And you see that there's an enhancement at small angle. However, if you change to gold, which have believed to have a relatively larger saturation scale, you see that very small angle, the energy correlator actually is suppressed. So this suppression behavior could be a signal of gluon saturations. But this is just doing some model calculation. It will be very interesting to actually measure it at the EIC. With that, I come to the end of my talk. I have shown you that the scaling behavior and plus the QCD factorization allows people to do a very precise measurement of strong coupling constant in jet structure. This measurement is enabled by measuring the slope of this nice scaling curve. And now we can also, with this observable, we can now imaging the hadronization transition from quarks to hadrons. That will help us understand the non-perturbative physics in this transition region. We can also start many physics in this, including non-perturbative and perturbative power corrections, and there's very rich theory and experimental data to be explored for high energy and higher point correlator, as well as for nucleon correlators. Thank you very much. That's
Two simple questions.
Yeah.
One is that you have given the evolution kernel for the operator O,
yes.
and you mentioned that is the same with the DGLAB. So what
Right,
are the
that's the same DGLAB, but it's in the timeline. It's actually the timeline DGLAB. Yeah, the moment of timeline DGLAB, if you want to.
what I'm saying is I want to understand why that is DGLAB kernel.
So yeah, the reason that this is DGLAB kernel is because the O is actually a Lie transform of twist2 operators. The enormous dimension, so this is actually the enormous dimension of twist2 operator. But you know that the enormous dimension of twist2 operator is actually the moment of DGLAB kernel.
So basically that is similar with the expanded twist2 operator. So
Yeah.
are they the same or they are similar? What I'm saying is for ordinary PDF,
Yeah.
we can make the OPE
Yeah, it's the same operator. Yeah.
the same operator.
Yes.
Okay. And the other question is on page 37, you have given the definition for this operator. N is the
N is the direction that your detector is sitting.
so that should have some correlation with the coordinate space coordinate y, right?
The correlated with what? Sorry.
Space coordinate y minus.
Y minus. So y minus is integrated over.
What I'm saying, n is related to this space coordinate or not?
So n is a spatial unit vector. It's a three vector pointing in that direction. So the n is basically is this direction. You should think of it. N bar would be parallel to y minus, basically.
That should be related to this the angle theta, right? So otherwise,
Yeah, n is related to the angle theta.
so really, back to my first question. So if I make this y minus to be Euclidean,
Y minus to be Euclidean.
yes, for instance on the z direction,
Yeah.
then
You are talking about boosting this
Yes.
y minus to the.
yes,
Yeah, but at the same time,
keeping
You
the angle
cannot-
to be the same.
right? But this operator is intrinsically defined on the light cone. So right now it's not clear how to boost it into a space line, Wilson line, or something. So that makes it difficult to put it into a lattice.
Okay, I will think about that. Thank you.
More questions?
Thanks for the nice talk. The question on the running coupling, maybe you can show slide 13.
13. Oh, 13.
13.
13. Is this one?
Yeah, and maybe the next one. Yeah. Is it? I'm surprised at how straight this.
How straight
this line? Yeah. So does the running?
Oh,
Is
so
does
the
coupling?
running coupling. So you look, it looks straight straight because it's plotting in a double log plot.
Yeah.
In reality, when you actually try to fit a strong coupling, you are do a template fit something. You
So
compute
does the
several
coupling
curves.
run with PT or with square root of x times PT, which is x?
Sorry.
Is
The
the
x-
argument of the running coupling is that?
The argument of running coupling is x times or theta times pt.
Yeah. Okay. Great.
Yeah.
So there should be. We should see some running in this.
You should, you will see
It's just
something
that it's
particular
not
when you are
very
close to the, when you are close to the lower end. Yeah. But because it's plotted in a double log plot, it's difficult to see that. And the and also at this energy, so this is at 600 GeV. The angle is like 0.1. So that's also 1060 GeV something. So that's actually running is not that rapid at that region.
So I have a question. So also from this plot. So this is completely for QCD, right? So
This is
suppose
complete-
yeah,
yeah.
suppose if I have some new physics, also couple of quarks, right? You will have it
Right.
will induce like a substructure, and so
Yeah.
that will change this.
Yeah,
plot a little bit.
so that's the one very usable point, but I didn't mention. This kind of observer is very useful to probe a scale in your physics. If you have, so the scale would correspond to theta. So this the transverse axis, the x-axis is theta square actually. The physical scale would corresponding to theta times e.
Yeah.
So this PT actually is the transverse PT. Sorry. So that if you have some particular physics happening at particular angle, you will be able to see as something like a bump or a kink in this
the
plot.
scaling, in the scaling region.
In this scaling region.
Okay.
In the case of heavy ion physics, there actually is experimental data, and people found that there seems to be a deviation when the angle is large enough, which means that the pattern is still in the medium. It has not yet get out of the medium. So it's able to probe the scale of the medium.
I see. Thank you.
Yeah.
So more questions? Okay, let's thank our speaker again.
Yeah.
Let's come back at 2:30, right?